So, thank you very much, and thank you very much to the organizers. Since this is the last talk of the conference, I'm allowed to say it was a beautiful conference, and also the school, I enjoyed very much. So, yes, I will talk about homotopy limits over a topos, or maybe I should have titled enriched homotopy completions enriched in a topos. So, you know that colimits can be generalized in two directions, a homotopical one and an enriched one. And so the goal would be to find a common generalization of these two notions in such a way that you can retrieve the ordinary notions by restricting appropriately. So you would like to retrieve homotopy colimits over the base given by sets, and then you would also like to retrieve enriched colimits, which are also called weighted colimits, by restricting your weak equivalences to just isomorphism. And the whole point of the talk is to not choose a homotopical structure on your base topos V, but rather one should pass to simplicial objects in V, where one should find a homotopy theory in simplicial objects in V that plays, in some sense, the same role as the homotopy theory of spaces plays over the base sets. So, first let me recall what are homotopical limits, and I will not give you the definition, but let's just think what they should do. One way is to think of them as models for infinity categorical colimits. So to reduce infinity categorical colimits to one categorical computations. But I think a deeper way, and also at the same time more elementary way to think of homotopy colimits, is just that they are the right notion of gluing when your categories have additional structure given by a fixed class of weak equivalences. And in fact, I think that every type of category theory can admit a relative version as long as you have subcategories, and then you will pass from colimits for that type of category theory to homotopy colimits. So for example, infinity categories are a type of category theory, and they have their own notion of relative infinity categories, and they have their own notion of homotopy colimits in infinity categories. So let me recall the construction over the base of sets. So if you have a relative category C with your subcategory of weak equivalences W, and you want to do the homotopy completion, what do? First, you do the ordinary co-completion. So you just take presheaves of sets. Then you take simplicial objects here. And then you must choose some notion of weak equivalence here. And you have, for every fixed object C, you have a simplicial set. So there is a natural notion because you have weak homotopy equivalences of simplicial sets, but you have also to include these weak equivalences that you had in C, and these will be maps between representables that also must be included in the weak equivalences. And in some sense, this way you obtain, so by a process that's called Bousfield localization, you obtain the homotopy completion of this relative category CW. So I claim that this is a general process that gives you homotopy completions also for other types of relative category theories, and I will just focus on the enriched. So for enriched relative categories. But you can also go to infinity categories and relative enriched infinity categories, and so on. So the important case to understand is the homotopy completion of a point. And as I said, the homotopy completion of a point, so if you work over sets, you are doing homotopy theory classically over sets, and you have the homotopy theory of spaces, which can be intrinsically characterized as the homotopy completion of a point. So now if you want to change the base to some topos, V, you will need to find, as I said, an homotopy theory of spaces over the base V, which will be on simplicial objects in V. And I would call the fibrant objects here can be complexes or V-spaces if you want. So when people put model structure on simplicial objects in V, the first way that they do it, and you find it in many books, is to look at just the underlying set. So you just map out of the unit. But this doesn't work because you are just looking at the underlying simplicial sets. This is too coarse. You are losing too much information. But there is one way that does the trick, and it is to look mapping out of every object in V. So you have a simplicial object in V, and you compose with this functor co-represented by V, and with these compositions, you obtain this family of simplicial sets, one for every object in V, and you define a map of simplicial objects to be a V fibration when the induced map of simplicial sets is a count fibration for every object in V. So let's see examples. So if you have a topos, you know that you have the discrete functor from the category of sets to the topos, which always has a right adjoint, but you can ask that it has a left adjoint. And when it has a left adjoint, you call the topos locally connected. And there is a notion of connected objects, a general notion of connected objects in a topos, that in this case is equivalent to asking that these connected components, that this left adjoint P0 sends E to the point. So this is really the connected components functor. And I would be even satisfied in locally connected toposes, every object is a coproduct of connected objects, but for me it would be already enough to have every object as a retract of a coproduct of connected objects. And to give an example, if you are in categories of presheaves over some index in category I, what are the connected objects? They are precisely the orbits of the category I. And so if you have, if I now is the groupoid associated to a group, these are precisely the orbits of the group. Why do I say this? Because in such a situation, whenever you consider simplicial objects in the topos E, I claim that there is a way to put a model structure on these simplicial objects in E by simply applying results of Dwyer and Kahn and Farjon, which I forgot to include, where you define the fibrations and the trivial fibrations by mapping out of every connected object. But since every connected object is a coproduct, every object is a coproduct of connected objects, this is exactly the same notion that I introduced previously of V fibrations, where you use every object. And so this is, in some sense, a concrete way to see this homotopy theory, but there is also more general results of existence of this model structure, which were proven very recently by Gambino, Ri, Sattler, and Zumilo, which work in any growth in the topos and even beyond. But I will not talk about this, but I wanted just to mention this work. So, in particular, if you take as an example the topos of G sets, and you can reformulate Elmendorf theorem as saying that if you start with the orbits of the group and you formally add all homotopic limits, you get the genuine homotopy theory of G spaces. But if you only start with a point and you add formally homotopic limits in the enriched sense, you get the same homotopy theory. So now I want to just mention some properties of this homotopy theory. So there is a classical theorem due to Dagger that says that over the category of sets you can build freely a homotopy theory from a small category C in the same way as you build a Abelian group or a module. This is the same thing, it turns out, as the homotopic completion of C. And there was some work by Dagger and Shipley for the case of abelian groups. They wanted to generalize this result to abelian groups. They have a paper on TAC, but they didn't manage to do so because they say in their paper that they do not obtain the full universal property. And so in some sense, as a sanity check from my point of view, I would like to have this theorem that works for abelian groups and for general basis. It works both for toposes and for in the additive context in some sense. These are the two contexts in which everything works fine. So the theorem will read as follows. Whenever you have an enriched diagram D from a small v category C into an enriched model category M, and I do not use the classical notion of enriched model category because I do not want to choose a structure on V, so it must be another one, which is just to ask that the weak factorization systems are enriched weak factorization systems. So this way you retrieve all model structure for V equal to set, but if you don't know what this means, it doesn't matter. So this diagram D can be extended along Yoneda by what I call this realization functor, which will be a left-Killen V functor that you can simply think as a V functor that preserves homotopical limits. And this factorization is unique in a homotopical sense because the space of factorizations is contractible. And moreover, something that I didn't write in the slides, but it's very important, is that whenever you have a weak equivalence of diagrams, the realization associated to them will be Killen homotopic. So this is really the homotopy invariance of homotopical limits. So from this, you obtain an enriched version of a classical construction of Dwyer and Kahn because you get mapping spaces. So if you just extend just an object chosen in the model category M, you get a right Killen V functor, so a V functor that preserves homotopy limits that gives you mapping spaces, but now they are not spaces, they are simplicial objects in V that are fibrant, so what I call Kahn V complex. And using the result, you can prove then that every enriched model structure in the sense that I said previously, the underlying infinity category is an enriched infinity category, and it is enriched in these spaces or Kahn V complexes. And then there is other two properties which I think are very important. If you compute the autoequivalences of this homotopy theory, you want it to be contractible, and in fact it is, in the same way as it is for spaces, or in some sense at the categorical level as it is for sets. And there is a result of Joyal. There is the over sets that generalizes to a base V. So whenever you have a topos, there is a very good notion of internal category and also a very good notion of internal nerve. And you can prove that whenever you have an internal category, this will be an internal groupoid precisely when the internal nerve is a Kahn V complex. So it is fibrant in this model structure. So this I already said, so let me skip it. And now to conclude, I want to instead to discuss what happens when you put a model structure on V. Because this is the main difference with all other approaches to enriched homotopical limits that already exist. The first one to study them was, in fact, Schulman, but there are others by Lakin-Rosinski and Vokrinek. So now let's assume a model structure on V. You have to make some assumptions. You have to ask that our objects are cofibrant. Let's just say that we choose a good enough model structure on V. Then you have this diagram. So on the right, you have V pre-shifts, just ordinary V pre-shifts with the enriched Yoneda embedding. On the left, you have simplicial objects in V pre-shifts. And for every choice of model structure in V, the theorem gives you this realization factor. And now, if you see this diagram, so here the upper triangle is just given by, it commutes up to isomorphism because this is just the weighted colimit factor, the ordinary one. Here you have the realization factor that I said previously, but here you also have the realization factor to M induced by this diagram D, given by the theorem. And this bottom one does not depend on the model structure on V, whereas this composition depends on the model structure. And this will be Killen homotopic to this composition. So to have the easiest possible example, let's take V equal to set, M any co-complete category, because you can put the trivial model structure. So the weak equivalences will be just isomorphism. And in this setting, if you compute what should be the homotopic limit, so the realization of a projectively cofibrant replacement of the point, since this functor sends it to the point here, this will be just isomorphic to the colimit, so you retrieve colimits. And something similar happens for enriched colimits, and you retrieve those two by restricting to isomorphism. So this is where I conclude, and I thank you very much.